Good morning. Today we are going to discuss about the next scheduling algorithm, the fourth in our track, that is round robin scheduling. So, as the name suggests, the processes will be handled in a round robin fashion. That is, you may have experienced in your childhood the musical chair competition. Yes. So, how will the participants participate there? They will be rounding around some of the chairs which has been placed, and everybody will get an equal, a fair chance to that chairs which are present there. But if suppose there are 10 participants, 9 chairs will be there. So that among the 10, 9 persons will take the chance and one will be coming out of the group. So likewise, we will be choosing the final one who is getting the opportunity of taking the resource. So likewise, a fair chance is given for the people who are participating in the competition. Likewise, here we schedule the processes by giving a fair chance to all the processes that are waiting in the ready queue, that have arrived in the ready queue, to get the hold of the process. So once when a process is getting execution in the processor, so when its time period it gets over, it is preempted, and the next process which is readily available in the ready queue, it will be given to the processor for execution. And there is a particular time quantum that is allocated in common, and all the processes will take the execution time only based upon that time quantum. So how much time quantum is given, that much time the process will be executed in the processor. And once the time quantum of that particular process it ends, then the process should come out, and it is preempted from the processor, and it is again placed in the ready queue. So at that time, if suppose the time at which a process is taken out of the processor and put inside the ready queue, at that moment, if suppose any other new process is coming in, then we will give the priority for the newly coming process first to be placed in the ready queue, and then the process which is being preempted will be placed in the ready queue. So this is how round robin scheduling happens. But the context switching is definitely, during the context switching, definitely the saving of the states of each and every process which is being preempted from the processor is of utmost importance, because once after a particular amount of time, again that process which is being preempted must be taken from the ready queue, and again it has to be allocated to the processor. So every state of the process should be maintained properly by the PCB during every context switch. So this has to be tracked properly in round robin scheduling. So with an example, we can see how the round robin scheduling works. So here we are having totally 5 processes, and each process is arriving at a different arrival time to the ready queue. So with respect to this arrival time only, we are going to allocate the process to the processor. Okay, so here we have considered the time quantum as 3 milliseconds. So now we can draw the Gantt chart. So the Gantt chart is plotted in this way. So when you see this, when you see the arrival time of the process, we can clearly see that process P1 it arrived at time 0. And since because our time quantum is fixed as 3 milliseconds, the burst time of the process is 8. But since the time quantum is 3, process P1 will be allocated to the CPU for execution for 3 millisecond of time. Okay, so from 0 to 3, P1 will be executing. So now you see from 0 to 3, that is for 3 milliseconds the P1 has executed. So within this 3 millisecond, what are all the other processes that would have entered into the ready queue? From the given data, it is clearly seen that P3 would have come inside, and the rest of the other processes it has not yet arrived. So P3 has come at time 1, at time 1 millisecond in the ready queue. So now the next process that is going to get the hold is only P3, because it has only arrived in the ready queue. So we will be preempting the process P1 after 3 milliseconds of time to the ready queue back, and then we are placing P3 for into the processor. So that is again getting executed for another 3 minutes. That is from 3 to 6 it is getting executed. So now at the end of the 6th millisecond, which process would have entered into the ready queue at time 5? P2 has arrived. So ready queue would have already it is having P1 with it, and now at time 5, because at time 3 we have preempted P1. So in ready queue we are having P1, and after P1 at time 5 P2 has arrived. So the ready queue will be maintained in the order as first P1 will be there, and then at time 5 P2 will be there. Okay, so now P1, the next process which is readily available in the ready queue is only P1 now. So P1 is taken from the ready queue and it is being given to the processor for execution. So again for another 3 seconds it will be executed. Okay, so now we have already preempted P3. So the order in which the order of the processes in the ready queue will be like this. That is first P1 and then P2 and then the currently preempted process P3. Now I'm talking about the 6th millisecond, right? Okay. So now P1 will again be given to the CPU. So now in ready queue P2 will be there and then P3 will be there. Okay. So P1 will be executing for another 3 minutes, and after that at time 9, which process would have come inside? P5 would have come inside at time 8, right? So now the order in which the processes will be in the ready queue at time 9 is first process P2 and then the preempted process P3 and then the incomed process, that is the process P5, and then process P5. After P5, the preempted process at time 9 P1, it will go and sit in the ready queue after P5. So the next process to get the processor is P2. So P2 is having a burst time of 2 only, not 3. So we are having the time quantum of 3. Okay, so anyway we have to preempt this P2 process from the ready queue. That is, we need to take the process P2 for execution. So P2 is being executed here, but its burst time is only 2. So from 9 to 11 it will be executing, and at the 11th second it will finish its execution. So the next process which is readily available in the queue is, I'm sorry, that is not P5, it is P4. I have told that at 8th millisecond P5 would have arrived, but before that itself we are having at the 6th millisecond P4 will be there in the queue. So P4 will be getting the process next, and after P4 will be again executing for 3 milliseconds, and after P4 for 3 milliseconds, and since P4 will also complete its execution, and after P4's execution the next available process in the ready queue is P3. So P3 we have already preempted and put in the ready queue. So P3 will be taking the hold of CPU from 14 to 17. So after this P5, that is the process P5 which is having a burst time of 5, which has arrived at 8th millisecond, it will take the hold of the processor. So from 17 to 20 P5 will be executing, and P1 it has already executed nearly 6 milliseconds of time. It has finished its execution, so it is having a remaining burst time of only 2. So P1 which is present in the ready queue, it will be taking the hold of the CPU and it will be executing, and after that the remaining the next process which is available readily in the queue is P3. So P3 will take the CPU's hold. So from 22 to 23 it will be executing. The reason is that already P3 has executed for 6 milliseconds of time, so remaining nearly only 1 millisecond of time is there. So therefore from 22 to 23 P3 will execute, and the last process which is available in the ready queue is P5, and P5 will be executing for the next last 3 milliseconds of time. So by 25 all the processes it would have finishes execution, and it will end the processing. So when we take the waiting time of each and every process, for P1 the waiting time is 0. Let's first see the completion time. So for P1 the completion time is 22, because P1 completely finishes its execution only at time 22, and P2 it has completed its execution at time 11, and for P3 completed its execution only at time 23. Okay, likewise for each and every process we have to find which is the execution, that is completion time, and we are noting that here, right? And from the completion time minus the arrival time will give us the turnaround time, and turnaround time is being noted, and the turnaround time minus the burst time will give us the waiting time, that is also noted here. So the average waiting time is found to be 10 milliseconds and average turnaround time is found to be 15 milliseconds. So the only the advantage we can speak about this round robin scheduling is each and every process without indefinite blocking or without any waiting, each process is getting a fair allocation. Each process is getting allocated to the CPU at a fair amount of time. Okay, fair in the sense equal amount of time. So that is the main advantage of round robin scheduling, and the main disadvantage is context switching is it is supposed to be happen frequently when compared to all the other algorithms. The context switching, that is switching of states between each and every process, is occurring again and again in round robin. So that it will create definitely an overhead of time, and the system it increases as the quantum switching it increases, the performance definitely decreases. So this is the main disadvantage of round robin scheduling. So the next class we can see discuss about the next scheduling algorithm. Thank you.